Well, now let's take a look at the question that followed example 5. In this last example that we did, at what points in this question did the concavity of the function actually change? When did I change from being concave up to concave down and vice versa? Well, what we can see is that if we're looking for points, of course we're looking for x comma y's, right? We're looking for the actual points on the graph. So I can see here that the concavity changed. The concavity changed at x equals 0 and at x equaled 2. So these correspond to the points 0 comma something and 2 comma something. Now, of course, if I'm looking for points on the original function, I would have to take the value of 0 and the value of 2 and plug them into my original function to get the corresponding y. Now, plugging in 0 is really easy here. Plugging in 0, I can see that I just get back 0. Plugging in 2 is a little bit more annoying. Notice 2 to the 4th power is 16. 16 over 4 would be 4. And then 4 minus 2 to the 3rd, which is 8, is going to leave me with 4 minus 8. That's negative 4 as a grand total. So these right here are, again, points, not intervals, but points on the graph where the concavity changed. Now there's a reason why we care about these points. We're actually going to give them a special name. We're going to refer to them as inflection points. So let's read this definition here. If I have a continuous function on an open interval that contains a point P, maybe like one of these could be a point P, if f changes its concavity at the point P, that is, like on the left side it's concave up, and then on the right it's concave down, or maybe vice versa. On the left concave down, right concave up. If the concavity changes, then we say that this point P is an inflection point. So let's go ahead here and take a look at example number 6. Notice that in this question we're being asked to find the inflection points of the function. Well, again, since inflection points are linked to changes in the concavity, to find inflection points again, I always have to go to the second derivative. Keep in mind, the second derivative so far is useful for finding concavity and inflection points. So let's go ahead and start to calculate this. We calculate f prime of x. Let's see, if I bring down the 5, I'm going to get a 1/2 x to the 4th. 4/3 x to the 3rd. This is going to be an x squared, and the 5 just disappears. We can also then jump to our second derivative pretty quickly here. Bringing the 4 down is going to leave me with 2x to the 3rd. Bringing the 3 down is going to be minus 4x squareds. And then finally over here plus 2x's. Okay, great. So I'm going to find some critical points here for my f prime. So that means I'm going to see that f double prime is equal to 0 when, well, 2x to the 3rd minus 4x squared plus 2x is equal to 0. So I got to work with this. Maybe I can do some factoring. There's definitely a 2 and an x in common here. It's going to leave me with x squared minus 2x. I guess just plus 1. So when would that be equal to 0? Well, I could probably do a little more factoring here with this inside. This is going to be 2x and the quantity x minus 1 squared. Oh, so this becomes really easy to see. This will be equal to 0 when x is equal to 0, or when x is equal to the value of 1. Great, so I have 2 different critical points here so far. Of course, I also have to check when my second derivative is going to be undefined. But since I have a polynomial here, this is never undefined. Okay, great. So now that I have this, I can go ahead and put all this information onto a number line. So again, I'm going to have my x's and my f double primes. I'm testing for inflection points and concavity. Oops, I don't need that many tick marks on there. I only need 2. I have 1 for 0 and 1 for 1. I know both these make the second derivative equal to 0, so let's test what happens on either side. So let's say I go to my f double prime. I'm going to use this factored form over here to help me compute things because it's a little bit easier. I'll notice again that my x minus 1 squared is always going to produce something positive, so it's really just whatever 2x does. So if I plug in a negative number, I'm going to notice here that I get negative, concave down. If I plug in something like a 1/2, I'm definitely going to get a positive. And if I plug in something like a 10, I also get positive. So keep in mind, this is not telling me where the graph is increasing or decreasing. It's telling me, because it's second derivative, where the graph is concave up and where it is concave down. So I have things that look like this. So now, since the question asked, what are the inflection points of the graph, I know that inflection points only occur when my concavity changes. So I can see here that an inflection point occurs only here at x is equal to 0, because that's the only time I changed from positive to negative or negative to positive. Over here at 1, I was positive on both sides. No change occurred. So at 1, there cannot be an inflection point. So now that I know this, I can say that this corresponds to the point. Again, I was asked to find an inflection point, so I need to find 0, comma, what? Well, again, if I'm looking for a point on the original graph, I would have to say plug 0 into my original graph, and that would get me the value of 5. So there we are. This is how I would find inflection points of the graph.